some political reasons behind why Python 2 or 3, but even skipping that, it's just for my own convenience, it's just to simplify things. So let's start with something very simple. I have some class. I want to do some kind of mathematical operation. I have some piece of software I write, and I have some class here that represents a polynomial. Some simple, linear polynomial with various coefficients, and I want to represent it as a Python object. And so I start with some code that looks like this, right? Class polynomial doesn't have anything interesting in it. And I can create two polynomials very simply. Right? And I might say P1 has coefficients 1, 2, and 3. Right? So this would be x squared plus 2x plus 3. And P2 has coefficients 3, 4, and 3. So this would be 3x squared, plus 4x plus 3. Okay? And I want to be able to do some simple things that we did in math class with these. I want to be able to add them. I want to be able to subtract them. I want to be able to figure out some details of them. The very first thing, for those of you who are relatively effective Python programmers, is you're going to look at this and you're going to say, why on earth did he write that in 4 lines when he could have written it in 2 lines? Why did I write this in 4 lines here when I could have written it in 2 lines? How would I compact my code here? So instead of constructing my 2 polynomials and then initializing the coefficients, I could initialize them all together. What would I do? I'm trying to get you to give me a little bit of feedback here. So what would I do? What am I missing here? My class has nothing in its body. What is it missing to allow me to do this a little bit more conveniently? A little bit louder for me. I need an init method. And so the very first thing when some of you look at this is you say, hold on, you're wasting our time here. You should probably want to have an init method that looks something like this. So you can write these lines much more tersely. And you don't have to have 4 lines when 2 lines would do. All right? So now we're happy. Whoops. So now we're happy. Now, if I run my code, and I'll split my screen, shrink this a little bit, and I'll maybe print out, actually I'll do this. So I'll run my code, and I have P1 and P2. And then somebody else looks at this and says, oh my goodness, printing out to the screen, that looks so ugly. What am I missing here? I'm missing another method. What am I missing? I'm missing a method that corresponds to what happens when I call this function at the top level, repr, to figure out the representation of my Python object. Yes or no? Yes. So what method do I implement up here? I have some method called repr. Right? So I have some method here that returns a string that gives me the information, gives me a printable representation of this class to the screen. And so I'll make this very easy. Like that. And so I'll run my code again. And we'll see, oh, there we go. Those are our 2 polynomials. Pretty straightforward. And we could make this print out a little bit prettier. We could see the x squared and the x and the constant term if we wanted to. But you can see this is a lot easier than just seeing the name of the class and its memory location. And we can continue down this exercise. Because the next thing I want to be able to do is I want to be able to add these together. And when I add them together, nothing happens. Python gives me an error. Unsupported operand types for plus, polynomial, and polynomial. But that doesn't make any sense. I know I can add polynomials. I did it all the time when I was in high school. How do I tell Python how to add polynomials? I have another method called add. And in my add method, I might return a brand new polynomial where I just give it all of self.coeffs, they're not coeffs, where I just zip together and add each of the individual items. So when I run that in my script here, P1 plus P2, it gives me a polynomial with 4x squared plus 6x plus 6. Now, what's the pattern that we see evolving here? For those of you who, off the top of your head, you didn't remember which of the underscore functions there are, for those of you who haven't ever seen these underscore functions before, you've begun to see some pattern. And what is that pattern? I have some behavior that I want to implement, and I write some underscore function. Some function that begins with 2 underscores and ends with 2 underscores. And for those of you who are Python programmers already, you might be familiar with these underscore functions. You might call them dunder methods or double underscore methods. Or if you find that word abhorrent, as I do, you might call it by a different name, data model methods. And you might say it's an absolutely absurd thing to call these data model methods. That's so many more syllables than dunder methods. But there's a reason I call them data model methods, which is, and I don't think I have internet access, but maybe I do. Oh, I do. If you Google for data model in Python, the very first or second link, depending on whether you use Bing, Google, or DuckDuckGo, will be a piece of documentation here that tells you all of these methods and what they do. But the pattern is a little bit more interesting than that. It's more than just having all of these methods on a single piece of documentation. It is that whenever we want to implement some behavior in Python, we want to tell Python, for this arbitrary object, do this behavior. Give me something that is a principal representation for this object. Perform some notion of addition for this object. We always see this common pattern. And the pattern is as follows. There is a top-level function or some top-level syntax. And there is a corresponding underscore function. The exact arguments that underscore function takes will be determined by whatever you find on this documentation page here. The default names of the arguments you can pick up off this documentation here. So for add, I called it self and other. That's just the conventional names for this. What each of these actually do, you can read from the documentation. But there's something more fundamental here. There's a pattern. When I want to add 2 objects, I implement add. When I want to initialize an object, I implement init. When I want to tell Python what to do, when you call repr on an object, I implement repr. We know in Python there's a function called len. It gives you some notion of the size of an object. What would it make sense for the size of a polynomial to be? What might that notion be? Any thoughts? The degree, right? The highest degree. So we want to implement this notion of size on this polynomial. How do we actually implement it? What's the name of the underscore function we have to implement? The one hint is there's usually a very close correspondence here. So what would it be here? Len. If we wanted the exact arguments and any of the caveats for how this needs to be implemented, we could look at documentation. There isn't anything special in the case of len. And we just return something like len of coefficients. So this would tell us the size of the polynomial in terms of its degree. And you can see these are both degree 3 polynomials. The pattern that we see is as follows. The Python data model is a means by which you can implement protocols. Those protocols have some abstract meaning depending on the object itself. In the case of a polynomial, to add them means whatever that meant in math class. In the case of a polynomial, to find its size means whatever that would make sense for the case of a math class. So it may make sense for us to know what the size of this polynomial is in terms of its highest degree. To get its representation, its principal representation, has meaning that's given to us by the documentation. The representation of any Python object is typically whatever string we'd have to type at the console to create another instance of that same object, and so on. In each case, this protocol exists. There is some underscore method that implements that protocol. There is some top-level function, like len or repr, or some top-level syntax, like the plus sign or the multiplication sign, that allows us to invoke that protocol. And it all fits together in this whole. We can think of this as a protocol in the sense that, like many protocols, when we implement something like len, we do that by delegating back to the protocol itself. So notice len is implemented in terms of len being called on a constituent object. Add is implemented by adding up some components, namely the coefficients. Repr is implemented by calling repr on some component. We see this as a very common pattern in the Python data model. Every time we want to implement some custom behavior on a Python object, we do it by implementing an underscore function, which ties to some top-level syntax or some top-level function, and we implement it in terms of that thing itself. So for example, if we have some top-level syntax, parentheses coming after the name of an object, and we might call that the call protocol. We'd implement it by implementing the function called call. We could look at the documentation to see any caveats or any special things we have to keep in mind when we implement that. In the case of a polynomial, this may not make a lot of sense. Perhaps to call it means something different. Maybe if we want to have some really horrible syntax where we say P1, P2 means multiplication, we could do that. I can't think of anything more atrocious than that, but perhaps that's what we want. But in any case, we may implement this in terms of calling something else. This is one of the core patterns that we see in Python. This is probably one of the very first patterns that you'd see as a novice Python programmer. In fact, when you look at object orientation in Python, there are 3 core patterns that you'd have to understand to really understand object orientation in Python. This is one of them, the protocol view of Python. The second one is the built-in inheritance protocol and how it works, where you go on a Python object to look for things. And the third one is some caveats around how object orientation in Python works. That's where I wanted to start off with. And for those of you who are just kind of on that level of being effective in Python, these are the kind of patterns that I would encourage you to look out for as you learn Python. I want to go much deeper than this. And I want to jump into a very tricky metaphor using a feature which you may have heard of and you may have been warned against, something you may have seen kind of along the margins when you're using some library. If you do anything with web programming and you use Django, you may have seen this in the ORM, or you may have heard people whispering about this one feature. And I want to bring up this feature for you. I want to show you that it has a very clear and concise meaning, just to illustrate how powerful these mental models are for understanding Python itself and for driving expertise. So let's shelve this for a second. Let's shelve this idea of Python having a protocol-oriented data model. And let's look into a new feature. I'll create a new directory called metaclasses, and we'll talk about metaclasses for a bit. Now, the gist of this tutorial is actually leading you towards 3 features which are far more common and far more interesting than metaclasses, namely decorators, generators, and context managers. There is a reason I want to start you off with metaclasses. It's a feature that everybody is warned against using. They're told it's magical, it makes no sense, it's totally the most complicated thing in the world. When in reality, it is the case of a feature where if you understand what the feature is really about, it is very clear and very obvious for why and when you use it. And it's something that you can kind of shelve away in your mind as, oh, this feature does this is why I want to use it. I don't